So welcome to today's Brown Bag Seminar Series, hosted by the Delta Stewardship Council Delta Science Program, along with our partners, the CDFW Watershed Restoration Grants Branch and the Surface Water Ambient Monitoring Program. Please silence your cell phones, and if you need to use the bathroom, take a key from the wall and exit to the left, and the bathrooms are down that way. Today's speaker is Dr. Sarah Yarnell. She is a research hydrologist at the Center for Watershed Sciences at the University of California, Davis. She earned her bachelor's degree in environmental biology and management from UC Davis, her master's in geology from UC Davis, and her Ph.D. in hydrologic sciences with an emphasis in surface hydrology and stream ecology from UC Davis. Dr. Yarnell's research focuses on integrating the traditional fields of hydrology, ecology, and geomorphology in the river environment. She is currently working with a broad coalition of academics, researchers, and resource managers to develop the California Environmental Flows Framework, which she will discuss with us today. This talk is the first of a three-part Brown Bag seminar series discussing flow targets and ecology. On Wednesday, July 12th, Dr. Eric Stein from the Southern California Coastal Water Research Project will be talking about a Southern California case study on setting flow targets, and in August, Dr. Carson Jeffries from UC Davis will talk about floodplains and the fish that use them. So please join me in welcoming Dr. Yarnell.
Great, thank you so much, and I appreciate you all having me here to come and talk about basically a larger scale project that is, as Nir suggested, is a coalition between a large group of folks, myself and others, Sam Sandoval and Belize Lane at UC Davis, folks at Berkeley, Ted Grantham, Eric over at the SQUIRP at the Southern California Coastal Water Research Project, folks at the Nature Conservancy, that's Julie and Jeanette, and folks at USGS, Larry Brown, and Jay over at the Watershed Center with us. And what I'm going to talk about today, this California Environmental Flows Framework, is something that we've been putting together probably over the last year. It started when several of us realized that we were working for different agencies, basically doing the same thing, developing environmental flows, and thinking about how to put into place more ecologically based flows in environmental flow works, and realizing that we were doing a lot of the same things. So we started talking to each other, and rather than work in parallel paths and repeating the same thing, we started meeting and trying to push forward a path that would be more inclusive across the state, more comprehensive across the state, and more applicable to multiple agencies at once. And so what I'm going to talk about today is this approach that we're coming up with, actively working with, and still actually developing here over the next year. So as most folks know, California is a huge diverse state. We have a lot of water problems across the state and many different types of questions related to water withdrawal and water diversions that come up. For example, how much flow can be diverted from irrigation due to irrigation ditches. In a lot of the urban areas, we have stormwater runoff that needs to be controlled or modified and then retreated, wastewater that needs to be treated, recycled, and then put back into streams, as well as seasonal restrictions on groundwater withdrawals. So all of these questions relate to water, but they can be very difficult to answer and might have a different set of ecological and environmental flow problems that can be associated with them. So the task is not simple. Oops. And then in addition to that, we do have areas that could be protected that are in better state than others, but it's hard to prioritize those areas knowing that there's going to be withdrawals and impacts that happen all across the state and all of the different watersheds. In addition to that, because California is so huge, there's a huge geomorphic and geologic topography and variability that happens across the state. And so even if you put one set of environmental flow restrictions in place for one type of use, that exact same pattern or prescription might not work in a different geologic or geomorphic area. So the same type of flow regime might not be suitable for different geologies, even if it is suitable for the type of water issue or water problem that you have. And so this has led to a lot of different approaches and a lot of challenges to actually creating environmental flow needs across the state. So as I said, we have this diverse state, and it can be hard to balance these needs with the broad range of demands that happen. And currently right now, there really is no mechanism for coordinating or information sharing among the public, but also even among the agencies. And so we have agencies that tend to have a different approach and a different set of standards to developing environmental flow criteria than others do. And so a lot of times what happens is two agencies or two groups come together to come up with a flow prescription for a particular watershed. They can actually have competing recommendations or competing prescriptions that end up then getting battled and negotiated over. So there really is a need for a coordinated statewide environmental flow framework to help deal with some of these issues. And again, as I said, many state agencies, State Water Resources Control Board, CDFW, even Forest Service and USGS affiliated with the FERC dam relicensing projects have a need to set environmental flows. But they might have different ecological endpoints, different species that they're focusing on, and different management needs. And again, not a way to really easily share that data or be able to communicate unless you happen to have the same people in the same room at the same time. So one of the things that our group, in talking with these different agencies and with the different groups, is trying to come up with a more cohesive approach to developing environmental flows. The idea is that most of us within this group that I introduced at the beginning are scientists, and so we tend to come at it from a scientific point of view. But from the beginning, let's start with what we know in a science-based approach about the hydrology of the different watersheds in California and the ecology of the different diverse species that we have, and combine those together to come up with environmental flow targets that are then based on the best-known science at this point in time. And so those are the 3 boxes there that you see circled in red. Based on that, then, if you can have a cohesive approach to developing those and a single set of flow criteria to start with, then you can develop into move into balancing the beneficial uses and really having a discussion that becomes more of a policy-based decision. So if there's a particular single approach to developing these flow targets and having a starting point to begin negotiations and discussions and taking into account these beneficial uses, then you have a simpler path forward into coming up with actual policy and regulations. Everybody's starting at the same point before they begin their negotiations, basically. And so what I'm going to talk about today is really a tiered approach to the first 3 bits there. So if I'm going to come up with a set or a guidance framework for developing flow criteria from which we start negotiations with, we have come up with a tiered approach to developing that. And there's a tier 1, which is the first bubble that you see at the top there, and a tier 2. The first approach is a single cohesive method, which I'll talk about in more detail here for the rest of this talk, to set core scale or broad flow targets across the entire state. And then, depending on the specific needs within a watershed, the geomorphology, the ecology, the particular agencies and stakeholders that are involved, you can then refine those flow targets using more site-specific e-flow methods that are more commonly used where necessary. And probably the most important piece then that we would emphasize is having a portal or a clearinghouse or a website and a place to share this data and have it be openly available and disseminated to the public and the various agencies involved. And we feel that by taking this approach, it allows, again, a series of steps that everybody can follow and agree upon to get you to a specific flow prescription then that can be specific for your site but starts from the same starting point. So these tier 1 or core scale e-flow targets then that I'm going to talk about for the rest of the time is something that, again, our group has come up with this approach to really be able to comprehensively have a single set or a single path forward, a methodology that can be applied across the state in a broad sense framework. It's a science-based analysis, and the 3 main steps that we have that I'll go through in a little bit more detail are to start with a single stream-wide classification across the state. It's based on the different hydrologies of the state and allows us to begin to group the different streams within the state into a series of types that then can be used to move forward to describe what the reference hydrology would be for that area. And to describe that reference hydrology, we've come up with this approach of what we're calling dimensionless reference hydrographs, and I'll talk a little bit more in detail about that. So once we know what type of stream type we're in and what type of reference hydrology it has, then we can look at a series of metrics or quantifiable components about that hydrology that we know then can relate to the ecology within that particular system. And this is sort of the functional flows approach that's based on a paper that got published a couple years ago that I'll also talk about in a little bit more detail. So using this rough guidance or this approach, we then can come up with some broad scale criteria that are functionally based for the ecology and hydrology of that particular system that provide a set of rapid or coarse or broad scale flow criteria that can then be refined with further environmental flow methods that are more traditional and used from that point on. So I'm going to go into a little bit more detail now about how this approach works. Okay, so the functional flows approach is based on a paper that was put out in 2015, and the idea is that it's a bioscience paper, Cliff Dahm and others are involved in it, is that there are particular aspects of the flow regime here in California that really serve a particular purpose or a function. And the idea is that we're not going to be able to replicate a full natural flow regime in our streams in California. It's just simply not possible with the over-allocation and the water supply infrastructure that we have. However, if we're going to restore aspects of that flow regime, which aspects are the most important ones that are going to drive the actual physical processes of what's happening in the stream? And so we want to focus on those components that support these natural disturbances, large floods that can scour and rework sediment, promote those physical dynamics that create habitat within the streams, and really drive then the resulting ecosystem functions that happen. And in our, as I'll talk a little bit more about, it's this dynamism and these physical dynamics within the streams that actually really drive the high biodiversity that we do have in the state. And so restoration of those processes can be the best thing that we can do given the confinement of a lot of our river systems. And then, of course, we need to take into account the actual geomorphic setting. And as Carson Jeffries is going to talk about next month, this dynamic between the channel and the floodplain, having the space for the water to actually do the processes is equally as important as having the water to actually move sediment and create those processes. And so we define then a functional flow as any component of the hydrograph that provides a distinct geomorphic, ecologic, or biogeochemical function. So we're not interested in replicating the exact pattern, the exact nature of that full function, that full natural flow regime, because we know that that's simply not possible in the water environment we have in California. But instead, let's focus on those pieces that we know through science-based literature and previous studies have a really distinct function. So, for example, in this hydrograph that I've shown here, this might be a typical hydrograph for a mid-elevation Sierra Nevada stream. We have a dry season that runs from July through October. You'll note that October starts here on the left. This is the water year. We typically have some small floods that begin in the fall when the rains first start coming in. You can have really large storm events that happen in the middle of the winter when we get our atmospheric rivers or large precipitation events coming down. And then as the snow melts from the higher elevations, there's a really pronounced, distinct springtime pulse. And so we might pick out particular components, in this case, these 4 components that are highlighted here, and say these ones serve a particular function. Let's work on preserving those and restoring those within our streams and allowing the rest of the flow regime to then be captured into a reservoir or dam or be allocated in the way that it currently is. And the other piece of this that you'll notice is that it's reflective of the natural patterns that occur both in space and time. So we don't want to release a peak flow down in the middle of spring when species are spawning. We want to try to match that natural timing that's occurring within the natural system. So let me talk a little bit about each of these 4 components that I've highlighted here, for example. So in fall, that wet season initiation flow is quite an important function in both that it provides ecological and biogeochemical functions. So it prepares the riverscape by clearing the channel bed of the organics. It's a flushing flow that goes through, reactivates the hyporheic zone, and really kickstarts a lot of those biogeochemical processes when you re-wet a stream after a low flow in the summertime. And we can see this out on the Cosumnes River, for example. There's a picture of those first fall rains coming down, spilling out of the channel and reconnecting with that riparian zone to really kickstart a lot of the processes that happen. In addition, this is also a cue for a lot of native species to start their migration upstream. In the Delta, we have the Delta smelt that are often cued by these fall flushing flows, but also in the north part of the state, a lot of the salmon species are cued to begin their migration upstream when these first fall flows come down. So there are both biogeochemical and ecological processes that are tied to this particular cue at this particular time. And so this might be a piece of the hydrograph then that we would put a lot of value on preserving or restoring within an environmental flow regime. The peak magnitude flows are really the primary disturbance that happens in our systems. These large floods that come down like we saw this year, we had 5. In some of our rivers that we monitor at the Watershed Center, we had 5 10-year floods that happened through some of the northern Sierra Nevada rivers with our wet year this year. And they completely redistributed, scoured, eroded, redeposited new sediment in all kinds of places. We saw a lot of willows and alders get ripped out this year that haven't been touched in the drought years. And it really resets that system and provides a lot of new habitat for the species to use. And really resets a lot of these successional processes that we know are really important in riparian communities. And so if you eliminate all of the peak flows by having that water captured behind a large dam and only allowing those peak flows to go down in the very wettest of years when they spill, you're really not allowing for that resetting of habitat that can happen typically on a 2 to 5 year basis. And so it's important to maintain the full magnitude of those peak flows. And in fact, we might argue that it's probably better to retain one large peak flow at full magnitude and skip and hold back the rest of the flows that are coming in within your reservoir than to reduce the peaks of, say, 5 flood flows and allow 5 moderate flows to come down. And so these are some discussions that you can have within a particular watershed and really debate, but you know, the merits of those. But having a full magnitude peak flow in the wetter years, or you know, every 2 to 5 years, can have a huge benefit geomorphically as well as ecologically within the system. And then again, these peak flows then, of course, are most effective when they have this space. So, for example, here's some pictures of the levee breaches that have been happening out on the Cosumnes River that some of you may be familiar with. And I can put a flood flow down a channel or a river channel like the Sacramento River, but if it's not accessing a floodplain and really moving that sediment around the floodplain, it might not have as much of an ecological benefit. So if we have a place where we can combine that peak flow with access to the floodplain, you're really getting the most bang for your buck and making that water work that much more for you in terms of restoring the ecological processes within the system. So the spring recession flow is also another important piece that there's been some good studies on in the last 5 years about how important this is, particularly for us here in California. So we have a distinct wet season and we have a distinct dry season, and this spring recession really is the transition that transitions you from an abundant, high-flowing river environment with a lot of water, cold water, down to the low, limited flows of summer. And if you are behind a dam and you shut off the spring recession, close the gates, and immediately go from a high-flow condition down to a low-flow condition with no transition between the two, you're fundamentally changing and altering the habitat that's down there in the channel. Allowing a gradual recession that has some amount of duration allows for quite a bit of ecology and geomorphology to actually happen within the system. So as the flows gradually recede, you're getting redistribution of the sediment that's been mobilized by the high flows. You're getting resorting of those sediment into different size patches that then create different habitat locations for different species. You're limiting the riparian vegetation encroachment by keeping areas wet and slowly drying them out, which delays any establishment of vegetation. And these annual cues, again in the springtime, are often the cues for out-migrating salmon or out-migrating fish, native fish, off the floodplain back into the channel. And so these species are looking for that receding, gradually warming, gradually receding flow to be their cue to move to a better environment within the summer. And so we would argue then that maintaining this transition between the wet season and the dry season provides a lot of ecological benefit. And then, of course, lastly, that all-important dry season low flow. There's been a lot of studies that talk about what the magnitude of low flows should be and maintaining that low flow amount that's in there. But I think what we would add to that is that it's really important to consider what the natural summer flows were like. Was that stream actually ephemeral, and have you changed it to a perennial stream? Or was that stream perennial and now you've changed it to an ephemeral? So we would argue for maintaining the ephemerality or perenniality of different streams in different systems to what they've been adapted to. And in a lot of cases, I would actually also, some of us would argue that going down to a lower flow in September is more adaptable for the species and more what natural systems would see if they have higher flows in the spring. So rather than maintaining a constant flow from June through August that's argued over and might have some set amount, how much do you need? Well, maybe in reality you need a little bit more water in spring, and then you can allow for less water in summer. I mean, our native species were adapted to a lot of dry years where you would go down to very low, very warm flows, but it was for a short period of time. And so if they're healthy and robust and have this spring water available to them, they might be then more adapted to being able to survive that refuge of the low, warm flows in the late summer. And so it's important then to consider this and take this into account when we're thinking about what those low season flows should look like. And then lastly, we would argue that maintaining this interannual flow variability is also equally important. California naturally has wet years and dry years, as we've all seen these last 5 years. We had the biggest drought on record followed by the wettest year on record. So these extremes naturally occur anyway. But again, the native species are adapted to this. A really warm, dry, low flow year might be a great year for macroinvertebrates and native amphibians and not such a great year for fish. But then conversely, a wet, cold year might be a really great year for some of the native fish species and not a good year for the amphibians. The biodiversity that California has, which is some of the highest in the West Coast, is based on these trade-offs and alternating these different types of niche and habitat habitat availability from these wet to dry years. If I have all dry years or all wet years, I'm actually going to have less types of habitat available overall. And so supporting the full biodiversity needs to allow for this interannual flow variability. And so what you can see here on this graph is that the idea is that if I maintain some of these components of the high graph, like some of the hydrographs, like these peak magnitude flows or these transition flows, within a single year, within a season, I'm allowing for different processes to happen, such as algal growth during the low flows or channel avulsion during some of the higher flows, like you see here on the graph, but also some years that have a higher peak magnitude or a lower peak magnitude from a wet year to a dry year, I might get different processes happening. So if we actually want to maintain the full suite of natural processes that occur in our streams, we need to have this interannual variability in addition to within-year variability, seasonal predictable variability that happens. And so, for example, here's what some functional flow regimes might look like with this interannual variability. We might still maintain all 4 components of that flow regime because we know that those are important, like I've just discussed, but we might change slightly their magnitude or slightly shift their timing depending on whether we're in a wet year or a dry year. And so the peak flows might be larger and of longer duration in a wet year because there's more water available, versus in a dry year you might have a much lower peak discharge that goes through in the wintertime. The spring recession in a wet year might be larger and later and have a longer duration, and in a dry year it might be shifted to more like late April, and it might have a smaller magnitude and a shorter duration. And this sort of reflects the natural variability that we see anyway happening within unregulated systems. And so, but you'll notice that none of these components have been shifted out of their natural window of timing. You know, we would not suggest putting down a peak flow in the middle of April or the middle of May when species are spawning. You want that really large peak flow that's going to move sediment to still happen in the wintertime. Okay, so how do we actually do this in practice? So that's the conceptual basis that we're building off of for the environmental flows framework and this Tier 1 coarse environmental flows that we're approaching. So the methodology then for taking these concepts and actually putting them into practice in streams is to focus on a particular stream class type, which I'll show here in a minute, taking the stream classification, knowing that we have a lot of different variety of streams in California, and developing what we're calling a non-dimensional hydrograph or a reference hydrograph for what the magnitude, timing, and pattern of flows look like in that particular stream class. Once we have that, then we can look at the statistical variability within reference gauges within that particular stream class and think about how the magnitude of the flows and the duration, how that variability changes within an unimpaired system. So, for example, if I'm interested in the fall flows that are going to cue migration upstream, that would be this box 1 here. I might look at a reference gauge or a reference hydrograph, and the bounds of that box, the upper and lower box, would be set by the variability of magnitude that we see across years within a particular gauge, and the sides of that box would be set within the timing, the natural range of timing that those types of flows occur. So by looking at the natural variability within reference gauges for a particular stream class, I can then define these boxes for these particular flow targets or flow components that I want to maintain, and this gives me a range of targets then that I can start looking at to negotiate within that box. So the timing can also be set by the aquatic species needs, so we can look at the hydrology and say that the fall flow might happen, typically, statistically happens between October and the 1st of December, and we know that delta smelt have a migration queue that needs to happen between the 1st of October and mid-November. And so that might guide where then we draw the bounds of that box for where we want that particular fall flow to occur. And then, of course, you can change within that box these flow targets based on a particular water year type. I might be in the upper part of that box in a wet year, and I might be in the lower part of that box in a dry year. So here's the stream classification that our group has worked on. Interestingly, we had one group at UC Davis developing a hydrologic stream classification for the state at the same time that SCWRP was developing, or Southern California Coastal Water Research Project was developing a stream classification for the state, both being paid for by the State Water Board, interestingly enough. This is how much the agencies don't talk to each other. So we've come together at the end of last fall. This is when we started talking to each other and realized that we needed to reconcile these two classifications. Another interesting point about this was that the UC Davis approach started from the hydrology and hydrologic methods and came up with a stream classification, and the SCWRP group started from biology and came up with how the biology impairment then coordinated with the hydrology, and there was 80% overlap between the two classifications, so which gave a lot of confidence that actually this classification is fairly accurate and fairly representative of the different types of streams that we have out in the state. And so then there was a decision framework that got put into place about how to deal with the 20% that had either one or two classes. And what you're seeing here is the reconciled classification between these two efforts that has 9 stream classes for the state. These are reflective of the catchment properties, the geology, elevation, and topography of the basins. The rainfall patterns, for example, you'll notice that the North State has a different stream class than down by LA. And the soil properties as well. One of the interesting things they found was that the percent clay and some of the riparian soils actually might have a slightly different impact on the hydrology that comes out. And so, for example, you can see that the yellow there is the snowmelt class. This would be the very highest of the Sierra Nevada, where the entire hydrology is based entirely on the snowmelt that happens. They don't get winter storms. The bulk of the water comes down those rivers in springtime when the snow is melting. The North Coast is what we're calling a winter storm class, and that has no snow. It's basically totally driven on the precipitation events that come through and hit the North Coast with the winter rains that come through. And so from using the stream class then, now we've come up with a way to assign all the streams in the state to a particular stream class that will have a particular type of pattern and range of variability of flow. And so, again, just a little bit more about the classification. So the stream classes have a variety of different hydrologic attributes to them. We looked at things like the timing of flow, the variability of range of flow, the relative magnitude. This graph on the lower left sort of shows you a couple of the stream classes and how different they might be. You'll notice the red line is pretty constant all year round. Well, that's a groundwater-driven stream that does not see a lot of seasonal variability in its hydrograph, versus the purple pink line that's at the bottom there is a flashy ephemeral-driven stream. This might be a lot of what you see in the desert regions and the dry Southern California regions, and you can see how much variability and magnitude they have between a flashy winter storm event that can have a very high magnitude and short duration and a really dry summer. And then based on these characteristics, it was a classification scheme that was based on the hydrology of the reference gauges. We can come up with a predictive model then based on those catchment properties, the geology, and the soil characteristics, and use that to then predict, using a GIS framework, then what the rest of the streams in the state might be and which class they come into. So just to reiterate, we used reference gauges, we have good unimpaired hydrology, assess the hydrologic attributes and geomorphic attributes, came up with the 9 classes using a classification stream, and then use this predictive model to then assign that class to all the streams in the state, and that's the resulting map that you're seeing here. Okay, so the dimensionless reference hydrograph then is a way to combine all the reference gauges in a particular class and to group those together to come up with a characteristic type hydrology or hydrograph basically for that stream class. So for example, those winter storms in the upper North Coast, what you're seeing here is on the y-axis is you take a particular gauge or hydrology for a gauge, and I look at the daily stream flow divided by the mean annual flow. So this allows for a way to non-dimensionalize all the different gauges that might be in that particular stream class and allow for comparison of the pattern, relative magnitude, and timing of flows for small watersheds and large watersheds. And so, for example, for that winter storm class, you can see that the bulk of the rain is falling in winter. These are Julian dates that are down there at the bottom. And it's very flashy. The relative range of magnitude goes all the way from 0 up to 25. So 25 times the low flows in the summertime you can actually see during the wintertime. And you can see that there's not much of a snowmelt signature. That rain is really coming down in wintertime in flashy storms, and then we have a long extended dry season low flow. Conversely, if I look at the snowmelt stream class, which is that yellow, really high elevation Sierra, you can see that that's really driven by the snow. There is little to no rain that falls in the wintertime because it's all falling as snow. But then once it warms up and that snow melts, there's a really pronounced, strong spring snowmelt pulse that's quite predictable. And you'll note that the range of variability there is only going from roughly 1 to 5. So the peak magnitude flow is only maybe 5 times what some of the lower flow is. Those relative magnitudes aren't quite as high, but there's a strong seasonal signal that's all completely tied into the timing of the snowmelt there. And then just for reference, here's an example of some of the other hydrographs for the different stream classes. This low volume snowmelt and rain, which is in the upper left-hand corner, is really similar to the type of hydrograph that I drew when I was talking about the functional flows approach. You can see that this is the mid-elevation Sierras where you're getting influence of snowmelt in spring. You can see that there's a quite distinct snowmelt recession that's happening there in springtime. But there's also these large peak magnitude flows that can happen in December that really move the sediment around in the streams. And so then based on each of these types of stream classes then, I might pick out different functional flow components that are appropriate to this stream class. So for example, the low volume snowmelt and rain might have all 4 of the components that I talked about for the functional flows approach, whereas the snowmelt, we might just be focusing on the peak magnitude of the snowmelt recession, and those low base flows, because that's what's applicable to this particular stream class. So we can then focus on quantifying those metrics using those dimensionless reference hydrographs and relate those to a particular ecological function. So for example, if I'm going to go back to that low volume snowmelt and rain class, representative of the hydrograph here, and I'm interested in maintaining those 4 components that I talked about, for example, I can use those reference hydrographs to quantify then the bounds on those box. And I might say, okay, so I do want a fall flush flow, I want it to cue, the fish migration, and I'm interested in what the peak magnitude or the range of magnitude for that fall flush flow is. Maybe I want to quantify that as a % over base flow and the timing of when that needs to happen. It should happen every year, and maybe it should have a duration of 2 weeks, or maybe it's 2 days, depending on what the hydrology of that particular class shows me. And so in this way, then, we're taking the information out of that reference hydrograph that we feel is appropriate to the ecology or the particular function that we want to maintain, and we're quantifying it using those non-dimensionalized hydrographs. And so, for example, here's a way that I might look at that. I realize this slide is pretty busy, but again, if you think about those 4 components, I have a range in magnitude here that I can calculate in Excel off of these dimensionless hydrographs, and I can look at the date that those first fall flows occur, the end date, and the range in magnitude that I see within a particular class. And the same with, the winter floods, and I can even look at what's a 2-year recurrence interval flood look like, what's a 100-year recurrence interval flood look like, what's the range in magnitude, what's the range in timing, what's the rate of recession that I typically see. And we're able to pick out quantifiable metrics that we can calculate off those reference hydrographs that I can then immediately put into an environmental flow framework. And just here's an example. We're calling it the functional flow calculator, but this is just to show you that we can take all of the reference gauge data in the state, run it through these algorithms, actually calculate these numbers, and use these numbers to actually define a functional flow target or an environmental flow target within a particular stream. And this is a zoom in on that aspect, and again, just to illustrate the point, if I'm interested in having a 10-year winter high flow recurrence interval in a particular stream, I can see from my non-dimensionalized graph that that flow for a particular stream might need to be between 700 and 2700 CFS. It should have a date of timing that happens sometime between November 1st and sometime in mid to late April. And its duration should be between 10 and 29 days, and it should occur maybe once every 4 to 9 or 5 to 8 years. And so these numbers are being calculated off of that reference hydrology, and we take that then and use that to create the bounds of what we want an environmental flow target to look like. And then we can do that for the different classes in the state. So I've got different reference gauges for each of the different stream classes, and I might have different ecological endpoints. So for example, in these low volume snowmelt and rain classes, I might be really interested in salmonid timing and macroinvertebrate diversity, for example. Well, based on those particular ecological endpoints, I might pick a series of quantifiable metrics from that hydrograph that I know from previous studies are relevant to those species. And then similarly down in Southern California, they don't have salmon that are migrating into the LA basin, but they do have native amphibians, and they're really interested in riparian habitat. And so for that, they might focus on a different series of metrics. Maybe they're more interested in the timing of when the spring flows come down to limit riparian growth, for example, and so that might be a slightly different metric. So I could potentially have different quantifiable metrics in different classes and for different ecological endpoints, but I have the ability to calculate any of those metrics from these reference hydrographs. So it in essence becomes one methodology that can be applied in a variety of different ways across the state. And so just to sum up, the idea with these Coarse Tier 1 environmental flow targets is that we're using a functional flows approach or concept to drive the methodology. That's the reasoning behind the methodology. And we're hoping to quantify and restore those components that have the greatest link to process. We know we can't restore the whole flow regime. It's just not possible. So let's pick the pieces that we think, based on science, at this point in time, have the greatest bang for their buck, basically. We're going to use these reference hydrographs from each hydrologic stream class to quantify metrics, which can then rapidly provide a range of environmental flow targets to choose from. And this then becomes a first cut at coming up with some environmental flows. Once we've got that box defined or those quantifiable metrics defined for a particular region, we can further refine that using more traditional environmental flow methods if necessary or if needed. So for example, if the flow range is too big or some of the stakeholders are not interested in having such a large framework, well, then we could do additional on-site studies, which typically happens, or additional like the Aloha approach or some of the other regional IFIM approaches to further refine those flows if needed. And then, of course, one of the key pieces that we all know but does not often happen is that monitoring is essential. A lot of these flows, we're doing our best scientific guess, we're doing studies based on it, but a lot of times you don't actually know if it's going to work until you go and do it for a while and actually see what happens. And so that's a big component and piece that needs to be included. And so with that, I'll end there and open it up for questions. Thank you.
Thank you. So my question has a little bit to do with implementing this. Let's say I was a reservoir manager and trying to decide how best to time my flows to support the downstream ecosystem. How do I know what kind of water year I'm dealing with, especially at the beginning of the season when we have those peak flows? A lot of those happen in January or December when we may not know yet what kind of water year we're dealing with. That, as a water manager, I would be wondering, if I allow this, large peak flow, how do I know that I'm going to get it back later in the year? So with a lot of these presumptions tied up in terms of the water year, how does that work in practice when, as we all know, we can have a really wet December and January and then things just shut off later in the year?
No, it's a really excellent question. And I think this is part of the discussion that needs to happen that it might end up being really specific for different locations. So, for example, a lot of my work has been in the FERC process up in the Sierra Nevada, and you might be more willing to let a December flow pass if you're in the upper reservoirs where they don't have as much storage capacity. They do have it's more common to spill in the upper reservoirs, and you might hold it for the lower reservoir until you know the water year type. I mean, typically the water year type gets declared March 1st to April, and if you know you're going to be looking towards a really wet year, then you might have to delay that flow that passes through the Central Valley. But historically, a lot of the flood flows in the Central Valley didn't happen until April and May anyway. So that type of question, then I think there's not a universal answer that can happen across the whole thing, and the management and implementation of that then has to go to the different sections that you're managing. The one benefit is that if you parse out in our water year types, our 5 water year types, at least you know the type of target that you're looking for, and as you get into February and into March and you start to have more confidence in what type of water year you're going to have, you might be more willing to then talk about, okay, it looks like we're going into an above normal year. We know we're going to be looking for some type of flow to pass that, could be of this magnitude, and you start to close in on that. But it's a really real question, and it does have to end up being decided on within that water year basis. And it's something they grapple with even routinely, not even trying to take these into account. How much water do I store and how much flood storage do I want to have? You're maybe just adding one more question into that. But yeah, it's a really good question.
So for part of your approach, you're using actual gauge data.
Yeah.
But how do you take into account, but you're trying to create functional flows, but I'm just wondering what your period of record is, and so a lot of your gauge data, it's been regulated for years, and it may not be regulated in such a way that's supportive of the ecosystem. So how do you take that into account?
Yeah, and thank you. I should have clarified that when we were talking about the stream classification. So the stream classification, 2 things. The first one is the idea is that this is providing information on the reference hydrology for those, not what currently is, but what do we assume and know that it should have been like or used to be like. So for that, then we had to go look for reference gauges. There's only 8 to 10 in the state that have more than about a 30-year record. But there are a lot of places where you might have a 20-year record from 1930 to 1950 before they built the dam. Or there's a 20-year record where we have naturalized flows where they've gone, they've gone through for various relicensing projects and recalculated what the flows are minus that. And so there was a process that actually both groups, originally I told you there were 2 groups that were doing this, both groups went through, defined their criteria for what would serve as a reference gauge, and made sure that they were taking into account as many gauges as possible, but those that really only reflected a reference hydrology. And so then using only that information, I think the final set of reference gauges is about 90 gauges across the state. And that information is available in the 2 papers that are associated with this. A lot of this information is hopefully going to be up on the web within another couple months. We're working with the data.cal.gov folks to get some of this information up. But that then defines the reference hydrology or type for that stream type. What you could do then is use the current data, the actual gauge data, to also do an analysis of impaired versus unimpaired. So how impaired is my particular stream?
So that's my follow-up question, just to be very clear. So when you're talking about those reference gauges, that's different than what a lot of people call unimpaired flow, right? Can you explain the difference?
Okay. Yes, so there are definitely a handful of gauges that truly reflect unimpaired flow. North Fork American, North Fork Yuba, there's a handful of them that are out there. They do not span the entire state, and they do not provide enough information to do a classification for the state. So a lot of the data then that we would consider reference is historical data, like I mentioned, a pre-dam date, or a naturalized flow, which is a modeled flow. And I was not one of the original authors on some of these papers, so I can't give you the laundry list off the top of my head of exactly the criteria they followed. But if it was a modeled naturalized flow, then there was a set of criteria that it had to pass in order to be included as a reference gauge. And I know not all of them are the gauges that come all the way into the delta, right? It's too complicated to really know an unimpaired or a naturalized flow directly into the delta. So a lot of these are the tributaries and the other streams in the state, not actually what's hitting into the delta. So we purposely didn't go there. It's too complicated, that one we know. So does that answer your question? Okay, yeah. And again, there are 2 papers that have been published off of the 2 original stream classifications. One is Pine et al. 2017, and the other one is Lane et al. 2017. And in both those papers, they talk about their criteria for selecting those reference gauges, and that was quite a big process to figure that out. How do we have confidence in which of these reflect the reference hydrology? But then the hope is that once you've coalesced that into a non-dimensionalized hydrograph, that's one of the reasons why we liked this approach, is it's giving you variability and timing and a pattern for a particular stream type, and now I can go forward, and there is an assumption that that particular stream might match that, but if I'm not confident in that assumption, then I can go out and do a site-specific study for that stream. But in general, we're going to accept that that is the rough pattern and the approximate course resolution for what the unimpaired hydrology should look like for that stream type, and then use that data to come up with some bounds on the flow criteria. And as a way to compare to the impaired, how impaired is my stream? Well, I can use that reference hydrology to compare to my impaired gauge data that I have.
Any final questions? Thank you very much.
Thank you.